We are the FHNW Rover team from the University of Applied Sciences, Northern Switzerland. And this is our rover Barbara.
Hi, I'm Melvin and I'm this year's project lead.
That was close. I'm Mario and this is Timo, and we are responsible for the safety of our rover and the team.
This is Julian and I'm also Julian. Together we are responsible for the financial and sponsoring part of this year's project.
I'm Noah, this is Andrea, and together we are the social media team and ensure that the rover can communicate to all the people over the world.
My name is Timo, and together with Julian, and Marco, we are the mechanical engineering team of this year's rover.
I'm Mario, this is Mario as well, this is Andrin, and this is Noah. And we are responsible for the electronics in the rover.
I'm Huki, this is Leo, this is Michael, this is Sandro, this is Simon, and together we are the computer science team.
Hi, we are the geoscience team. My name is Carla, and together with Melanie, I'm doing the science part. And we are supervised by Ferle, Gabriel.
At the ERC 2025, we had a difficult time, as some of our key systems didn't work properly. Despite that, we had a wonderful time in Krakow, exchanging the spirit of engineering with teams from all over the world. Nevertheless, this year we are highly motivated to get back to the podium again, with a lot of new innovation we want to discuss with the other teams. We already showed in this year's preparation competition Rover Treff that our key systems are functional again and our team is full of fire. We hope we can bring this fire to the finals of ERC 2026.
Our rover can drive forward, backwards. The rover can turn to the right and to the left. Our rover can drive slopes upwards and downwards. The rover stops immediately after the emergency button is pressed. The rover chassis forms the structural backbone of the entire system. It integrates the frame, electronics and mounting system into one compact and robust platform. The chassis supports the drivetrain, ensuring stability and mobility across uneven terrain. The linkage system improves force distribution and helps the rover maintain stability during operation.
At the heart of Barbara's science capability is our fully redesigned 6-axis manipulator. Actuators for the 3 distal joints have been relocated to the base and are connected via a Bowden cable system, dramatically cutting distal mass while almost tripling available torque compared to our previous design. The result, 900 mm of reach and easily 2 kg of payload.
A cam-driven steel ball locking system secures each tool with over 15 kg of tested retention force. The conical interface guarantees docking with minimal precision, while pogo pins provide both power and CAN connectivity directly to the tool. The standard gripper offers dual motor control, integrated time-of-flight sensing, load cells and is able to handle loads up to 2 kg, while the shovel gripper uses a worm gear for non-backdrivable jaws, ideal for regolith and maintenance tasks.
The rover's power distribution consists of a dedicated PCB with 9 separate channels that can be switched independently over a CAN interface. In order to comply with our safety philosophy, each channel has its own protection. In the event of a board failure, the plug-in PCBs can be swapped quickly and operation can be resumed in a matter of minutes.
At the core of our rover, there are two custom Jetson Orin NX baseboards, designed entirely in-house. Built as a high-density, multi-interface platform, the board consolidates vision, communication and high-speed I/O into a single compact design. It replaces multiple legacy modules, reducing wiring complexity while improving signal integrity, bandwidth and overall system robustness.
Here we see our dashboard integration. We implemented various pages, for example a video stream view, ROS diagnostic and direct integration to our sensor and actor bus system. We have digital twins of our manipulator and drivetrain to simplify rover operation.
We achieve autonomy through a two-tiered approach. For the high-level task planning, we use NHN and ROS to ensure reliable deterministic orchestration. For low-level execution, we rely on a vision-based deep learning model, providing the system with highly precise and nuanced control over its physical actions.
Our drone can fly upwards, downwards, to the back, to the front, left, right. We can land our drone manually. Once we turn off our remote control, the drone auto-lands.
This is our drone Mellifera. It is a hexacopter with a custom aluminum frame and a carbon tower holding all the electronic components. We use a Pixhawk 6C flight controller and ensure stable flight with an optical flow sensor.
The system uses several MATLAB toolboxes including the computer vision, image processing, parallel computing and UAV. Communication with the drone is handled through PX4. The autonomous mission workflow consists of takeoff, localization, exploration, target detection and autonomous landing while generating a first report.
Now, our manipulator grabs a tool. After successfully grabbing our tool, we now perform the surface sampling task, first with a stone. The stone is now put into our load cell, and after successfully weighing, we now continue with the regolith sample. After unloading and weighing the regolith sample, we continue with our deep sample. After our successful drill attempt, we now tear our load cell and unload the sand into the container. Then we measure the weight of the sample. To demonstrate the astrobiology tool, we first prepare our well-deserved after-work beer as a reference solution. Then we measure its pH value.